Samuel, you can say hi to the audience.
Hi.
Yeah. So I need Samuel is right now is a computation science in Brookhaven National Lab. So he has his background in physics, but he also have a MD degree before. So Samuel was the first wave on the software implementation for quantum circuit and reinforced learning back to 2018 to 2019. And right now, his research is rely on how to apply this quantum enhanced machine learning on both classical and quantum data. And please welcome Samuel and his talk on the quantum enhanced machine learning. Thanks.
Okay. Hello, everyone. I'm Samuel from Brookhaven National Lab. And in this talk, I will introduce the basic idea of quantum-enhanced machine learning and how to do it. I will mainly describe idea of hybrid quantum classical model and the variational quantum circuit, VQC, which is the building block of such computing framework. Then I will briefly present some of the recent quantum machine learning applications based on the VQC framework that I mentioned. So here is the outline of this talk. First, I will provide some background on the near-term quantum computers. And then I will introduce the most important building block of such computing framework called the variational quantum circuits or the hybrid quantum classical paradigm. And then after we introduce the necessary notations and preliminary knowledge of the VQC, I will present some of the recent quantum machine learning applications. And then I will point out some potential future research directions. Okay, so quantum machine learning can be divided into 4 categories based on the algorithms they use and the data they process. The CC represents the classical data and the classical algorithms. This is actually not the quantum machine learning, but the conventional machine learning that we use every day. And the CQ represents the using a quantum algorithm to process the classical data. And this one is particularly interesting nowadays because most of the data that we have are classical. Say your speech data, your text data, your images, your videos, and many others. And the QC represents for using the classical machine learning to process the quantum data. So actually, this is using the classical machine learning to study the quantum physics. This area is mainly in the academia. So physics can use the machine learning to learn the data from physics, from quantum experiments. And this one is particularly challenging because the quantum data generated from the quantum systems are potentially very hard to be processed using a classical computer. So that's why we need to build a machine learning model based on the quantum algorithms and quantum computers. And finally, the QQ represents for using quantum algorithms to process the quantum data. And this is the most advanced but unexplored area because quantum algorithms and quantum machine learning methods are still in its very early stage. So we don't have many tools to deal with the quantum data. In addition, we don't have a very powerful quantum machine at the moment, so it is very hard to directly process this quantum information. In this talk, I will mainly cover the CQ part, namely that using the quantum machine learning algorithm to learn the data, the distribution from the classical data. Okay, so recent progress in the quantum computing hardware brings many new possibilities, and there are many expectations that quantum computers will solve a lot of challenges. As you may hear, many people say that quantum computing will help us solve the climate change. The probably you may heard someone trying to use a quantum computer to find the cure of COVID-19 and many others. And there are also some practical applications such as using quantum computing to do the high frequency trading and many other financial transactions. But these are just expectations. Near term, quantum machines are with certain limits, as I will explain. One of the big challenge is that the current quantum computers, the so-called noisy intermediate scale quantum computers, usually are without the quantum error correction and cannot perform the fault-tolerant quantum computing. This means that this quantum computer usually with limited number of qubits, so they cannot implement large quantum systems, and it's sometimes very hard to demonstrate the quantum advantages. Another one is that these quantum computers are only with limited circuit depth. So if you implement a quantum algorithms or quantum computation problem with a very deep circuit, then these noisy quantum computers cannot faithfully carry out these computations. So many famous algorithms, such as the most famous one, the Shor algorithm, cannot be faithfully implemented on existing quantum computers. So to leverage the capability of these machines, we need a specific set of design to design these algorithms which are implementable on these machines. One of the method that we can use to leverage the capabilities of the near-term quantum machines, or the NISQ, are the so-called variational quantum circuits. So we will introduce the hybrid quantum classical paradigm here, which is based on the VQC. This particular kind of algorithm is suitable for currently available NISQ devices. The idea is that a certain part of the computation will be performed on the quantum computer, while the optimization procedure is carried out on the classical computer. With this framework, we can easily apply the optimization methods, which is highly developed in the classical machine learning community. For very complex quantum machine learning architectures that I will describe later, instead training on a real devices, we can also train or test this model using a quantum simulation software with high performance backend. Okay, so let's introduce the VQC block. The VQC, or variational quantum circuit, are a very special kind of quantum circuit with parameters tunable via the iterative optimizations. These optimization procedures are mainly in the gradient-based or the gradient-free method. Here, the U block is the quantum circuit block for encoding the classical data X into a quantum state. And the V is the variational block with learnable parameters set up to be optimized by the gradient or gradient-free method. Finally, the quantum measurements are performed over some or all of the qubits, depends on the problem that we are trying to solve. The measured values can be further processed with other quantum or classical functions. The first step in the variational quantum circuit is to encode the classical data into a quantum state. So first, we introduce the basic idea of what a quantum state is. So consider a general n-qubit quantum state can be represented as follows. So the psi is the linear combinations of all the basis states, and the C with some subscript C is the complex amplitude for each basis state, and each state is 0 or 1. So if you have n qubit, then you have q to the power of n bases. And here we need to mention that the q square, the c square is the probability of measure a specific state. So the total probability should sum to 1. So the encoding method is a routine, a quantum routine or a quantum circuit, which can transform your input data, which is a classical vector, into a set of these quantum amplitudes. So there are several quantum encoding methods, but the most general one choose are the amplitude encoding and the variational encoding. So let's talk about the amplitude encoding first. Okay, so given a vector, the alpha 0 to alpha 2 to the power of n and so on. So there are overall 2 to the power n values. So we want to encode this state, this vector into a quantum state. The most intuitive form is that we encode these states directly into the quantum amplitudes. So we can imagine that we have a circuit. Actually, there is a circuit to encode these values directly into the quantum amplitudes. We also need to mention that these vectors should be normalized first, because as we mentioned earlier, the total probability is 1. And there's a great advantage theoretically that n-dimensional vector will require only log 2n qubits to encode. Although there is a great advantage in terms of the model size or the number of parameters, but in general, it is difficult to encode classical vector directly into the quantum amplitudes, because the circuits used to perform this procedure is pretty deep, so it is not that useful in the near-term devices. Another encoding method is called the variational encoding. So the idea is that directly put your input numbers x1 to xn into the quantum circuit. Use these numbers as the rotation angles of a quantum gate. And there are so many potential quantum gate sequence to achieve these results. Here I put one example. For example, here we have the rotation y and the rotation z. And we put the x1 to x4. Okay, we made some transformation on the x1 to x4 and use these transform values as the quantum rotation parameters for this gate. So the initial state is the O0, the 0, 0, 0, 0. And then this quantum state will go through these rotation gates, and so it will be transformed into another state in the Hilbert space, and then the variational blocks will operate on this state to get the results that we want. Although this method it seems that it cannot provide such great parameter saving or model size reduction compared to the amplitude encoding, but it is much simpler to implement and is very suitable for the existing devices. Okay, so after introducing the quantum circuit, variational quantum circuit block, let's talk about what it can be used. So since we have very powerful classical machine learning tools, we don't want to drop them, and we want to leverage the best part from both the quantum and the classical world. And the hybrid quantum classical paradigm can actually help us achieve this. Here, I present one of the example. So here, we have some quantum nodes and the classical nodes. Yellow box, as you can see, are the quantum nodes with a small quantum computer. And the blue nodes are some neural networks or mathematical functions to post-processing the results. Then we can combine these nodes into a very large framework in a graph. And we can train the model in an end-to-end fashion. So this idea is pretty much the same as the one used in the modern deep learning, which can power a very large and complex architecture. So the idea is that both of the quantum nodes and the classical nodes are combined into a directed acyclic graph. And if you have a graph, then you can define the computational graph and how to do the back propagation through this model. But we know how to calculate the gradient across deep neural network, but we don't know how to calculate the gradient over a quantum node yet. So the next step is that how can we calculate the gradient across a quantum node? If we have this method, then training a hybrid quantum classical model is just like the ones that we use to train a deep neural network, a classical convolutional neural network. Okay, so let's recap some of the ideas of the variational quantum circuits. So the variational quantum circuits includes three components. The first is the encoding component, and the second is the variational component, which will be optimized with a certain kind of gradient descent method. And then we will do the measurement. So let's go this step by step. So first we have a zero state, and then we go through the encoding state, which is the U0 here. And the encoding state only depends on the input value X. So we have the encode state UX operate on the zero. Then we go through the variational parts, say the UI. So okay, we only consider the only one of the operator. Okay. We pretend that the other three are not there for simplicity. And then finally, we calculate the observable to have the expectation values or the measured results. So we have a vector or a number depend on the number that you perform, the number of measurements that you perform. So actually, this is a quantum function. That's how it's generated. So there is an input value, an encoding circuit, and some parameterized circuit. So we can have a vector or a number. And then it's shown that the gradients of such quantum functions can be calculated as this. So the idea is that you need to prepare two circuits, each circuit with a slightly different parameters. So for example, if we want to calculate the gradient of f with respect to the parameter I, the theta I, then we can construct two circuits and we load the same input vector x, and we have shifted the parameters, namely the theta I plus pi over 2 and minus pi over 2. And amazingly, this formula can give us the analytical gradient of the quantum functions. So we have the knowledge of calculating the gradient of a quantum function, then the whole backpropagation framework can work seamlessly with the classical models. After having this powerful method, we can look into some input applications. So the first, the most famous one, and I think is the first variational quantum circuit-based work is this paper, Quantum Circuit Learning Framework, from the Mitarai School. And in this paper, the authors showed that we can use such variational quantum circuit-based method to perform nonlinear classification problems and several kinds of function approximation. So, for example, in the right-hand side, the authors show that the variational quantum circuits can be used to learn these concentric circle classification test. And in the left-hand side, it's shown that such VQC-based models can be used to learn several functions such as the x absolute value of x and y equals x squared. Then we can use these variational quantum circuits in a more advanced way. Imagine that you have a classical convolutional neural network. And in the classical convolutional network, there are several circuits. There are several neural networks to perform the convolutional kernels. And these convolutional kernels will scan over the input images. And there's an interesting question that whether it is better to using a variational quantum circuit to replace these classical neural networks. And as the experiment showed, it can provide certain advantages over the classical convolutional neural networks. The advantage is that when you limit the number of parameters in both the quantum and the classical network, say they have a similar model size, then it can be shown that it can be shown in numerical experiment, numerical simulation, that the quantum convolutional neural network can perform better than the classical ones. The better means that learning faster or reach a higher accuracy. And another implementation is that we can use certain kinds of the classical preprocessing to help us reduce the dimension of the classical vectors. For example, in this work, classically graph convolutional matrix is used to pre-process the image, very sparse images from physics experiments, and we use this convolutional filter to aggregate the features of the input image, and then use the amplitude encoding to encode such images into the quantum circuit. Surprisingly, it performs much better than the old classical models when the number of parameters are similar. It can also provide comparable performance to the quantum convolutional neural network that we just mentioned. However, with this a hybrid approach, the number of parameters is further reduced. So we can show more potential quantum advantages that are interesting. Another way to preprocess the classical information into a quantum circuit is to use a quantum-inspired classical algorithm. Here, in this example, we use the quantum-inspired tensor network to compress a large dimensional input data. Different from the previous example, this quantum-inspired tensor network is parameterized. So there are some parameters in this tensor network, as well as some parameters in the variational quantum circuit. So this model is trained in an end-to-end manner as the computation graph that we just showed in the previous slide. The overall model can be trained simultaneously, and we found that using the numerical simulation, such method performs much better than the classical counterparts, such as the PCA with the BQC. So this learnable feature extractor performs much better than the commonly used principal component analysis. And this method is it can be used to many other applications when the input image or the input data dimension is much larger than the capacity of the quantum computers. Next, we want to talk about the federated quantum learning. So actually, when training a machine learning model, we may probably have some privacy issues. The privacy issue is mainly that we don't want to share our data, but we don't have enough computing capabilities. And so there are several parties, and each party has their own data, but they only have a very small scale computing power. So can we leverage this limited computing power and the distributed data to reach a high performance model? This is the federated learning, one aspect of federated learning. And this is a very hot topic in the classical machine learning. So we also want to study that whether these privacy aspects can be considered in the quantum learning. So here we provide a hybrid quantum classical model, which can be trained, distributed across many different parties. In this framework, the local data set is not shared. Only the trained models are shared and aggregate and distribute to these parties. Notably, the performance in using the quantum federated training is comparable to the non-federated learning one. And second, since we can have comparable performance with non-federated learning, so it is expected that we can leverage such method with several small-scale quantum computers that we have these days. In the machine learning, recurrent neural network are designed to process sequential data. The general idea is that given an input x at a time step t, the output at time t is fed back into the neural network to predict the next time step t plus 1. It means that the model can keep some form of the earlier information, retaining certain memory. However, the classical argument suffers from some problems. For example, its performance goes down when the temporal dependence is too long, and it's very hard to train due to the vanishing gradient problem. In the classical machine learning, long short-term memory is a modified form of the recurrent neural network to fix these issues. The basic idea is that it processes the cell states to keep track of the long-term dependency and reduce the vanishing gradient problems. In order to perform the quantum machine learning, there is a quantum-enhanced form of LSTM, which the classical neural networks W replaced by the variational quantum circuits. The VQC blue box will do the job that the classical neural networks do. And we keep all other components from LSTM as classical, including the cell state and the nonlinear activation function, so that we can still do fan out and bypass the limitations of no cloning theorem. We consider a damped simple harmonic oscillation that obeys the second order ODE. We observe that the QLSTM can capture the pattern much faster than its classical counterpart when the number of parameters is similar with just one apple. Also, we noticed that the classical LSTM has a very hard time capturing the correct equilibrium 0 point, which QLSTM has no problem even after only a single apple of training. Then, since we can use the VQC as the function approximation, and so one of the interesting application is that putting such VQCs into the to learn the value or the policy function of the reinforcement learning problem. So the reinforcement learning is an agent that interacts with the environment to learn the decision-making policy. So if we put such function approximations, which we believe that or is been shown using several numerical simulations that such functions have a better expressive power than the classical models, then can we use such quantum circuits, quantum models to better learn a decision-making process, a decision-making problem? So the idea is that we use the classically proven machine learning or reinforcement algorithms such as the deep learning, the policy gradient, and many others to train a quantum model interacting with the classical environment. And it is shown that the classical model can achieve very good results in certain testing cases. Although this is a very early stage research, but it showed that in certain problems, the variational quantum circuit-based models can achieve very good result while the number of parameters is largely reduced. We will have another talk in this tutorial series to explain the quantum reinforcement learning in very detail. So based on this background, so we can have some potential interesting questions in the quantum enhanced machine learning. So currently many quantum advantages are only shown in certain cases. So can we provide many more applications and demonstrate quantum advantage in more practical or real world using scenario? And can we use the distributed training to train the quantum machine learning model, either to leverage large scale parallel computing or in the privacy preserving AI aspect? Then there is a large area to study the theoretical foundation of the quantum machine learning model training and the convergence and many others. If we have a good theory, then probably we can have a better understanding of how to design a good content machine learning models. And finally, since these are content machine learning algorithms, what we want to do is to train these content machine learning models directly on the quantum computers instead of quantum simulators. So probably in the near term, when the commercially available cloud-based quantum computing platforms are more mature, then we may have more opportunities to study in these directions. And then I acknowledge my support from the Brookhaven National Lab, LDRD programs, and the US Department of Energy Office of Science. Thanks for your attention.
Yeah, thank you.